If you clicked on this video, it's probably because you've heard things like entropy is the level of disorder in a system, or entropy always increases and the universe tends toward chaos. These statements are pretty common, and of course, it's true that total entropy always increases. It's the second law of thermodynamics. But the disorder bit? Not so much. Just take a look at this. What you see in these tubes is a colloid, a liquid with tiny balls of polymethyl methacrylate floating in it. Each tube has more balls than the last. If we could observe what's going on inside that liquid, we'd see the little balls bouncing off each other inside a giant pinball machine. No surprise there. The researchers let the jars sit, but after a day had passed, they noticed something odd. Each tube had turned a different color. It couldn't be a chemical reaction or anything like that. The balls were stable. They reached a surprising conclusion. A pattern was emerging in the liquid. The balls were arranging themselves equidistantly. The more balls in the tube, the less distance between them, and the light was giving them away as dispersion only occurred with wave frequencies that fit this pattern. A few days later, a structure had already emerged. We can see crystalline and vitreous forms appearing inside the tubes. You might think they just settled that way, that the balls gradually drifted to the bottom of the tube and somehow fell into place. But look at this container. Glass had formed at the top of the tube, defying gravity. This is mind-blowing. Without force, without any external stimulus, simply left to its own devices for a few days, the colloid arranged itself into an organized structure and formed a crystal, a hard sphere colloidal crystal. This can also be simulated. Put a sufficient number of solid balls in a box, shake them up, and if you wait long enough, you'll see that they transition from rave mode to a pattern all by themselves, from disorder to order. Well, where's your chaos of entropy now? In this video, we'll explain how the heck this is possible and why your physicist pal is wrong to assume it violates the second law of thermodynamics. In fact, it confirms it. But don't be too hard on your friend. Until the 1950s, hardly anyone thought this was possible. To explain, we need to go to the very heart of entropy, the interpretation Boltzmann gave us. This video is the first of several produced in partnership with IFIMAC, the Condensed Matter Physicists Center, where we'll talk about the fascinating and often overlooked science behind materials. To begin, we're going to cross the dividing line between thermodynamics and statistical physics. We'll stop visualizing systems as a whole and start analyzing the countless tiny elements they're made of. And I think there's no better way to reveal the true identity of enigmatic entropy than a magnet. Magnets have magnetic properties because they're made of smaller magnets, mini-magnets, so to speak. These little magnets are actually the atoms and particles that make up the material of the magnet. But to keep things simple, let's just call them mini-magnets. These mini-magnets can point in any direction, but again, for the sake of simplicity, let's assume they only have two choices, pointing up or pointing down. This network of little magnets can arrange itself however it wants in infinite possible configurations or microstates. And of course, that freedom of orientation changes the magnetism of the whole. Mini-magnets are so tiny that our instruments can only measure the sum of their magnetic fields. In other words, the magnetism of the entire magnet. For example, if this mini-magnet is pointing away from its companion, their magnetic fields will practically cancel each other out. But if they're pointing in the same direction, their magnetic fields will be reinforced. You add up the ones facing one way, subtract the ones that are facing opposite, and that gives you the magnetic field we can measure from the outside. This is the macrostate, which has a certain value. But nothing in nature stays still, and mini-magnets are no exception. They can spontaneously change direction. In ferromagnetic materials, usually they are all correctly oriented because each mini-magnet is influenced by its neighbor's magnetic field. But turn up the heat, give those little magnets some energy, and the forces among them won't be intense enough. Now each one will remain as it is or reverse its direction at random. Both options are equally probable. We've got thermal fluctuations. So here's a question. If I have a magnet with a magnetic field that measures 12 units and set it on fire, what will happen? How will its magnetic field and the position of the mini-magnets change? Think of it as a board game, where each square represents the different internal states of the magnet, a board with thousands of squares. We start on the square where all the mini magnets are pointing in the same direction, but since we've turned up the heat, the state is about to change. In just a second, the magnet will jump from here to another square. We don't know which because they all have the same probability. One jump is just as likely as another, and once it lands on the new square, the system will jump to another, and on it goes, leaping erratically around the board. There doesn't seem to be much more to say about this, but remember, we've only been focusing on the little things, on what the microstate is like. What happens if we look at the macrostate? Imagine that we measure the magnet, and the meter indicates it's at a full throttle, the highest possible degree of magnetism. There are 12 mini magnets, and we measure 12 units of magnetic field. Question: how are the mini magnets arranged inside? Well, if just one of them had flipped around, the magnetic field wouldn't be at maximum strength, so this means that all the mini magnets must be pointing in the same direction. It's the only possible configuration. But this situation is rare, because what happens if we measure the pieces of magnetic field and find that it's 10 units? Things aren't so simple anymore. 10 units means that one of the mini magnets has flipped and is canceling out another. So where is that reversed mini magnet? It could be here, or here, or here, or here. There are 12 possible microstates that could create the same macrostate. And the lower we go, the more complicated it gets. If I measure 8 units, that means there are 2 reversed mini magnets, which could be placed like this, like this, like this, like this. There are a lot of possible configurations, 66 to be exact. 66 different microstates can produce an 8-unit macrostate. We find the ultimate complication in a macrostate with 0 units, where half of the mini magnets are pointing up and the other half are pointing down, canceling them out. There are tons of ways to create this 50-50 situation, nearly 1,000 different microstates. The pattern is obvious. The lower the magnetic field I detect, the greater the number of microstates I find. When you look at all the possible configurations of mini magnets, there are far more ways to produce something that's basically an ordinary rock than to create something that will stick to your fridge. And this is a key piece of information. All we have to do is classify the squares on the game board. On this board, there's only one square with 12 units of magnetic field, but there are 12 squares with 10 units, 66 squares with 8, and so on. This gives us a kind of pyramid, and we can see there's a pattern of behavior. The magnet will almost certainly jump to the lower levels, and usually it doesn't climb back up. Maybe a little bit, but it almost always descends again. There's a very simple explanation. Because jumping to any square is equally probable and there are oodles of squares at the bottom of the pyramid, it's almost certain that the jump will be to squares on lower rather than higher levels. Is it possible to jump from a lower square to a higher one? Sure, but it's less likely for the simple reason that there are fewer squares, fewer microstates. Specifically, the probability of jumping to or staying in a macrostate with a null magnetic field is 1/3, while the probability of returning to the maximum magnetic field is just 0.2%. Now imagine the situation when instead of 12 little magnets, you have millions upon millions of them like in a real magnet. The probability of keeping all those mini magnets aligned is ridiculously low. So if I start out with a magnet that had a high magnetic field macrostate, thermal fluctuations will cause that magnetic field to diminish, most likely ending up around 0. You can grab a ferromagnetic magnet and a lighter and test it yourself. When you heat it up, you'll find it doesn't stick like it used to. When you increase the temperature, it seems like some invisible force compels the system to move down the pyramid, but in fact, it's just probability. And here's where entropy is hiding, because entropy is just a fancy word for the number of microstates. A macrostate with few possible microstates is called a low entropy state, while a macrostate with many possible microstates is called a high entropy state. The magnet tends to move down the pyramid, so we can say that a low entropy system tends to evolve toward a high entropy system. Entropy always increases, simply because systems tend to move toward their most probable macrostate. So there you have the second law of thermodynamics with magnets. As you can see, it has nothing to do with order or disorder. It might seem like the system passes from an orderly to a disorderly state, but this is a subjective perception. Look, if you take the mini magnets and arrange them to form a dragon's head, you'd say that they're neatly ordered and have very low entropy, but that doesn't make much sense. First of all, because entropy isn't something you can associate with the configuration of mini magnets. You associate it with a macroscopic property like the total magnetic field. Having a dragon shape isn't something I can see from the outside. Entropy is a property of macrostates, not microstates. And secondly, even if this weren't the case, the magnetic field of the dragon is practically zero, so it would just be one of the many microstates with a null magnetic field. And as we've seen, the entropy of a non-magnetized macrostate isn't exactly what you'd call low. Basically, order and disorder are not good words for describing entropy, no matter what the dictionary says. And this brings us to the hard spheres. How does this idea explain the formation of this crystal? Well, everything we've just seen applies. Systems evolve toward macrostates with a greater number of microstates. So, is a hard sphere crystal created because its formation increases the number of positions accessible to each sphere? That was the key, and it took physicists decades to find it. Think of it this way: if you try to cover a table with plates by placing them willy-nilly, you'll find it hard. In all likelihood, some of the plates won't fit. You'll have gaps that are too small, and you'll need to remove a few. The plates only fit on the table when they're all arranged in an orderly fashion, so in this case, order allows more elements to fit on the table, optimizing the use of space and giving you more microstates to play with. The same thing happens when you put a lot of hard spheres in a box. If there were only a few of them, and if they were just dots, we wouldn't be talking about this. Being organized in a pattern is far more improbable than being placed at random. But now those dots have volume. They don't let other balls overlap with them. They collide, and those collisions eliminate many of the microstates we could think of. For instance, look at that gap. There's not just enough space for another sphere to fit. These are microstates that are being wasted. But when the spheres organize, crystallize, and optimize the space around them, the number of microstates skyrockets. The more volume each sphere can have without colliding with another sphere, the greater the number of possible configurations. And the way to achieve this is with order. In other words, if we look at our landscape of possibilities, we see that the disorganized colloid is at the top and the crystal at the bottom. Time does the rest. Crystallization induced entirely by entropy. No forces or interactive energies, just pure probability. But in the real world, in other systems, chance isn't everything. There are interactions and forces that control its evolution, pushing the system toward the macro state it should be in. So, maximizing entropy isn't everything. Minimizing its energy is also important. We might say that energy and entropy are the actors that control our fate because we are complex systems. That's why unraveling the mystery of entropy isn't just a question of satisfying our curiosity. Entropy plays a fundamental role in life, in packing molecules like DNA or proteins, in the spontaneous formation of viruses, and it doesn't just affect colloids. It can even tell us how to store rice or wheat grains in silos. That's why some scientists at the Condensed Matter Physicists Center, IFIMAC, are paying close attention to this sophisticated statistical game because it gives them an increasingly profound understanding of how this soft matter organizes itself and occasionally reveals how to make better simulations. This could be the solution to many mysteries of biochemistry. But getting back to entropy, a word of warning, there's a hole in this interpretation of the second law of thermodynamics. A little crack that could mean this law isn't inviolable and that unimaginable things are real. But we'll look at that in the next video. And remember, if you want more science, just hit the subscribe button. Thanks for watching.